Hello, my name is Kevin Judd, and I'm a researcher in Jonathan Gamel's Estimation, Search, and Planning Group in the Oxford Robotics Institute at the University of Oxford. This video presents our work on multi-motion estimation, particularly with respect to the challenges posed by occlusions in complex dynamic environments. I'll first discuss the background and motivation behind multi-motion estimation and the various challenges involved. I'll then discuss our past work on multi-motion visual odometry and introduce our recent work in addressing occlusions. So first, a bit of background. In robotics, especially mobile robotics, a crucial task is accurately estimating motion from a sequence of observations from a dynamic sensor. This analysis tends to be focused on either determining the motion of the sensor, referred to as its ego motion, or the motion of other third-party objects in the environment, but is rarely concerned with doing both simultaneously. Our work looks to explore how both of these tasks can be unified in a single approach to determine every motion in the scene at once, including the sensor ego motion. And it is easy to imagine how this could be useful in dynamic scenes that move in complex, unexpected ways. Various approaches have been designed and extensively studied to address parts of these motion estimation challenges. Visual odometry, or VO, estimates the motion of a camera relative to its static environment. Simultaneous localization and mapping, or SLAM, similarly uses observations of the static portions of a scene, as well as some external ego motion input, to develop a globally consistent map of the environment and track the sensor's location within it. Object tracking is a field that seeks to consistently track independent objects, usually from predetermined object classes and often within the images themselves, focusing on their real-world motions secondarily. Optical and scene flow are dense techniques that calculate the translational motion of every pixel between two images or stereo frames. These techniques are all useful for estimating certain aspects of the motion within an environment, but struggle to address many of the challenges posed by complex, real-world environments. For example, VO and SLAM can struggle in dynamic, unstructured environments, and significant effort has been spent on robustly isolating the static portions of a scene, but that intentionally ignores the other independent motions in the scene. Multi-object tracking techniques focus on multiple independent motions, but are often restricted to a set of known object classes. And both tracking and flow-based techniques rely on simple motion models that do not apply to complex, non-planar motions, especially with significant rotations. To further illustrate this, here's a standard sparse VO pipeline. Consecutive images are usually processed by detecting salient image features and matching them between the images. The dominant motion in the scene is isolated and assumed to belong to the static background. All outliers, either from sensor noise or other dynamic motions, are rejected and ignored. The inliers to that dominant motion are then used to estimate the trajectory of the camera. Here's an example of how this would operate in a dynamic environment. As the dynamic platform moves through its environment, sensor observations are taken at each time step. Observations corresponding to independently moving objects will not fit the dominant motion model and are rejected. The pose of the platform is estimated from the remaining inliers, and the process repeats for the next time step. Over time, the ego motion trajectory of the sensor platform is estimated from these estimates, but a huge amount of information about the dynamics of the environment is ignored. Our work on multi-motion estimation explores those motions that other techniques reject in order to estimate the trajectories of all the motions in a scene. To do this, we must address the chicken and egg problem, where estimating each independent motion requires a segmentation of points with similar bulk motion, and segmenting points accordingly requires a set of motion estimates to do so. Our previous work, Multimotion Visual Odometry, or MVO, directly addresses this chicken and egg problem. At a high level, the multi-motion estimation pipeline looks something like this. It proceeds similarly to the traditional VO pipeline, but instead of isolating just the dominant motion and rejecting everything else, it simultaneously segments all the bulk motions in the scene and estimates them independently. MVO extends the traditional VO pipeline using graph-based multi-motion segmentation techniques. It is able to decompose a scene into its constituent SE3, or rigid body, motions, and simultaneously estimates the camera ego motion with the other motions in the scene. It also operates directly on 3D points, so it's agnostic to the type of 3D sensor used to generate those observations, as well as the size, shape, and number of objects in a scene. Here's an illustration of how the pipeline operates. As the sensor platform moves through the scene, dynamic objects that would have been rejected by a traditional VO pipeline are instead segmented and estimated simultaneously with the sensor ego motion. The result is a set of trajectories corresponding to each independent motion in the scene. Here's an example of the segmentation and trajectory estimates from our work at IROS in 2018. All motions are estimated as full SE3 trajectories. The black points on the static background correspond to the ego motion estimate, and each other motion is estimated simultaneously with it. The original pipeline did have some limitations. It is a sparse, feature-based technique, so it can track motions through some partial occlusions, given that enough features are still visible on the object. However, it is not robust to full occlusions, where no direct observations are available. Similarly, it employed a discrete time estimator that could allow for discontinuous or impossible trajectories, especially when partial or full occlusions complicate the scene. In order to explore the challenges involved in multi-motion estimation, we needed a dataset with ground truth trajectory data for both the sensor ego motion and the third-party objects in the scene. Unfortunately, no existing real-world datasets were sufficient for this type of metric multi-motion evaluation, so we set about designing and creating the Oxford Multimotion Dataset, or OMD. The OMD consists of several complex dynamic scenes, each focused on a particular challenge inherent to multi-motion estimation, and includes ground truth trajectory data for every object in the scene, collected from a Vicon motion capture system. The sensor data was collected from multiple sensor archetypes, including stereo RGB and RGBD cameras, as well as an IMU. Many of the results shown here are run on segments from the OMD, and if you're interested in using the OMD for your own research, you can find it on our website. The work presented here expands on the original pipeline to address the challenges posed by occlusions. We do this by applying continuous time estimation to the pipeline. This introduces motion priors to the estimator that incentivize smooth transitions between the states. This prior can also be used to extrapolate and interpolate estimates when they aren't directly estimated. This means we can use the prior to extrapolate motions when they become occluded, and then correct those extrapolated estimates through interpolation once the object becomes unoccluded. The motion prior we use is the SE3 white noise on acceleration prior described by Anderson and Barfoot. This extends the traditional estimation state to include SE3 velocities in addition to the SE3 poses. These velocities are modeled as locally constant by modeling the acceleration as a zero-mean Gaussian process. We apply this prior to the original MVO pipeline to track and estimate multiple motions through occlusions. This yields greater robustness to sensor noise and allows for motion-based tracking through occlusion, but is only accurate as far as the prior applies to the true object motion. So if the object drastically changes velocity by accelerating or changing direction, the estimator will perform poorly. It is also important to recognize that the prior is only valid in an inertial frame, and a constant velocity relative to one frame may not be constant relative to another, especially if that frame is moving. The Occlusion-Robust MVO pipeline is structurally similar to the original pipeline, operating on 3D tracklets and being agnostic to how they are generated, and it outputs the trajectories and segmentation for all the motions in the scene. Likewise, it initially proceeds similarly to MVO, using graph-based multi-motion segmentation techniques to extend the traditional VO pipeline. The segmentation is cast as a multi-labeling problem, where each motion is represented by a label. Motion models are iteratively proposed, re-estimated, and merged until the segmentation converges. It estimates multiple egocentric trajectories simultaneously without making any assumption as to which corresponds to the true ego motion. After the segmentation converges, any remaining outlier points or spurious labels are sanitized before re-estimating all motions in a geocentric frame. Unfortunately, the continuous time ego motion estimator defined by Anderson and Barfoot cannot be directly applied to estimate the other motions in the scene because the motion prior must be expressed in an inertial frame rather than the non-inertial egocentric frame. We can approximate an earth-attached frame as being quasi-inertial for this purpose, but the continuous time estimation problem must be re-derived to estimate third-party motions in a geocentric frame. Please check out our paper for more details on how this is done. The newly estimated geocentric motions can then be contextualized among the motions previously observed in the scene. In situations without occlusion, this is a straightforward association. However, in the presence of occlusion, the motion-based tracking routine, called motion closure, can be used to maintain trajectory consistency without relying on object appearance. Motion-based tracking relies on the accuracy and expressiveness of the motion prior to accurately track motions through occlusions, meaning it is robust to changes in appearance which can cause predefined object detectors to fail, but fails if the object changes direction or otherwise does not move according to the prior. Motion closure proceeds as follows. If a motion is no longer observed, it is extrapolated forward in time using the motion prior. Motion closure seeks to determine if a newly discovered trajectory actually corresponds to a formerly occluded motion. This is done by comparing the new and extrapolated trajectories through a motion-based metric using both position and velocity. If the trajectories are sufficiently similar, the motions are closed, meaning the extrapolated estimates are corrected to where the newly discovered trajectory was first observed, and the intervening estimates are corrected through interpolation. The rest of the new trajectory is then appended to the corrected interpolation. The resulting trajectories remain consistent through the occlusion as shown here on a challenging occlusion segment of the Oxford Multimotion dataset. Note that the block tower in this video is effectively occluded whenever it comes to a stop because it temporarily becomes part of the static background. The Occlusion-Robust MVO pipeline relies on two fundamental assumptions: that objects move rigidly and with locally constant velocity. While these assumptions don't exactly describe many objects and motions in the real world, in practice, they are good approximations for the vast majority encountered in mobile robotic applications. Many non-rigid or piecewise rigid objects, such as pedestrians or cyclists, have bulk motions that can be approximated as rigid. Similarly, the white noise Gaussian process model for acceleration means that objects with non-constant velocities can still be accurately modeled if they accelerate or change direction smoothly. The fact that MVO is sensor agnostic, operating directly on 3D points, means that it can be readily applied to different sensor archetypes. We are currently working on extending MVO to event-based sensors, which are particularly exciting for motion analysis because they measure pixel-wise changes in brightness in an asynchronous high-rate stream. This means they inherently measure the dynamics of a scene, only recording measurements of the parts of the scene that change and achieving effective frame rates in the tens of kilohertz. The novelty and uniqueness of this sensor data also pose a variety of new challenges for robotic vision algorithms. Despite these challenges, we demonstrate that our MVO pipeline is applicable to this type of data and is currently a focus of ongoing work. So, to summarize, Occlusion-Robust MVO extends the original MVO pipeline using a white noise on acceleration motion prior. The prior is used to continuously estimate the SE3 trajectories of every motion in the scene, as well as extrapolate them through occlusions. Motion closure is then used to track these motions through occlusions when they reappear. The pipeline is demonstrated both quantitatively on sections of the Oxford Multimotion dataset and qualitatively on real-world rigid and piecewise rigid motions, as well as on data from different sensor archetypes, such as event cameras. Thank you for your time, and please find links to the Oxford Multimotion dataset, as well as some of our other work on our website.